this session, we take interest to deal with a new topic, namely differentiability or derivability or differentiation. First of all, let us understand the purpose, rather exact meaning of the word differentiation. Differentiation. In one word to speak, a rate change is just nothing but differentiation. More precisely, very more precisely, imagine that this is a conical flask in which water is present. In which water is present. At this end, say a small nozzle is provided so that water flows down. And here is, you please imagine, the Lord Shiva. Is here. Water is being poured from this conical flask. It will have a radius of the base and the height of the water column, slant height, so many factors are there. You see, continuously water is flowing on the Lord Shiva. If you want to measure the amount of cc flowing on Lord Shiva per minute, or the rate at which it is being conducted, the so-called Abhisheka is conducted, you have to measure the rate of flow of water. The flow of water is nothing but the rate at which the radius of the column changes or the height of the water column changes, like that. Therefore, change in one particular quantity with respect to another quantity, if it is under discussion, then the concept of differentiation comes into the fray. Well, let f of x be a function. Y is equal to f of x be a function. There has been a change in the independent variables, say x. X may change to x plus h, you imagine, x plus h. Then y changes to f of x plus h minus f of x. F of x plus h minus f of x. What is the rate change? Change in y by change in x. For the sake of perfect measurements, if you want to take the limit as h tends to 0 of f of x plus h minus f of x by h, this is of course called the derivative of f with respect to x. Derivative of f with respect to x. Of course, this is a triple radius, height and slant at 3 variable function it is. We shall speak of it later in the partial differentiation, of course. But I have used this example justly to mean the word differentiation only. Let us now come to the conceptual and theoretical part of this differentiation. Let phi not equal to S subset of R. that is S is a non-empty subset of R. Let f from S to R be a function. Be a function. Let A be a limit point of S. By this word we mean that every neighborhood of A contains infinitely many points of S. If limit as extends to A, f of x minus f of A by x minus A exists, if limit as extends to A, f of x minus f of A by x minus A exists, then we say that f is derivable at x is equal to A. And of course, this limit, this particular limit as extends to A, f of x minus f of A by x minus A is called the derivative of f at x is equal to A. And this limit is called the derivative of f at x is equal to A, denoted by f dash dA. Denoted by f dash dA. So this is the theoretical and conceptual definition of the derivative of f at x is equal to A. Let us be brief. Let us be very brief in this expression. F is derivable at x is equal to A. To mean that, we must seek the existence of this limit. If this limit exists, then f is derivable at x equal to A. So likewise, continuity, derivability is also a local character. F is continuous at x is equal to A. We generally speak just like that, f is derivable at x is equal to A or not. And in this particular definition, if you take A as x and x as x plus h, then f dashed x is equal to limit as h tends to 0, f of x plus h minus f of x by x plus h minus x is h. Yes, both the definitions give us the same sense. This is of course derivative of f at particular point A, and this is the derivative of f in general at x. F dash x we say, f dash x, and this we say f dash A. And there are so many symbols to represent this derivative. Let us have a look over that. In particular, if y is equal to f of x, then is denoted in any one of the following ways. One is f dash x y dash d by dx of f of x df by dx f dash d of f of x, d of y, etc. And the most familiar dy by dx, etc., etc. But of all these, this is very frequently used. What do you mean by dy by dx? D by dx of y. This entire d by dx of is a unit, it is a function derivative of y with respect to the variable x. That is, we are going to learn the change in f of x corresponding to the change in x. Related to the change in x, we are about to find the change in f of x, that is y, that is dy by dx or dy by dx of f of x, like that. These are the various symbols. Well, let us now go into the details of this concept. Just like one-sided limits, we are to learn, we are to go through one-sided derivatives also. What are they? You see, basically a derivative is nothing but again a limit as h tends to 0 or limit as x tends to a, like that. As it is a limit, it is generally provided with both one left hand limit and right hand limit, and those limits are of course termed as the left hand derivative and right hand derivative, and it is more precise to say that limit as x tends to a from left of f of x minus f of a by x minus a is denoted by f dash a from left. And this is called left hand derivative, LHD at A. Of course, this can again be taken as limit as h tends to 0 f of a minus h minus f of a by h. F of a minus h minus f of a by h. Similarly, right hand derivative. What is say about this? This is therefore f dash dA from right. F dash dA from right. One thing is very evident, just like in the case of limits. In the case of limits, we said that both left hand limit and right hand limit exist and are equal, then only we say that the limit of the function exists. Just like that here also, f must be derivable from left, that is left hand derivative should exist. F must be derivable from right, that is the right hand derivative must exist. And both those two derivatives, left f dash dA from left is equal to f dash dA from right. Then only we say that f is derivable, and the common derivative is of course called the derivative of f at x is equal to a. In short tips to say, f dash dA from left is equal to f dash dA is equal to f dash dA from right. If such things happen, then only we say that f is derivable at x is equal to a. If only this limit exists, then f has the left hand derivative at x equal to a, or f is derivable from left at x is equal to a. If only this limit exists, then we say that f right hand derivative of f at x equal to a exists, and f has the right derivability at x is equal to a, like that. If both of them exist and are equal, then we say that f is derivable at x equal to a, and the limit is f dash a. Yes. You can trace all these things from the knowledge of limits even. There also we could proceed in the same way. We shall now take interest to look at some more important properties of differentiation. Number one of them is, if f is derivable at x is equal to a, implies f is continuous at x is equal to a. So derivability implies continuity. But you see, continuity need not imply derivability. That is a concept of great importance. Surely we shall come across so many numerical examples in which it can be used, of course. Well, let us now try to confirm this. It is true or not. Should we believe it? Or is there any theoretical background? Let us try. Let us try. It's a very simple proof, one single line proof. That is why I like to deal with that. Look here. Proof. Let limit as x tends to a, f of x minus f of a by x minus a is equal to f dash a. With what authority I am able to write this step? Because I am given the information that f is derivable at x is equal to a. So therefore, I am given to understand that the limit as x tends to a of f of x minus f of a surely exists. That is why I am naming it to be f dash a. Let it be like that. What do you like to prove? F is continuous at x equal to a. Okay, you recollect all the three conditions which are required to say that f is continuous at x equal to a. F of a must be defined, of course. Unless or otherwise, you cannot use it here. Number two, limit as x tends to a f of x as x tends to a exists. And number three, limit of f of x must be f of a. Okay, by combining all these three conditions, I am considering limit as x tends to a f of x minus f of a. Let us see what happens. Is equal to limit as x tends to a f of x minus f of a by x minus a into x minus a. I think you have seen what I could have done. I have just multiplied and divided with x minus a. Now, this is therefore equal to limit as x tends to a f of x minus f of a by x minus a into okay, what is this limit? F dash a. Who told you? He has given in the data. Therefore, it is f dash a, and that is of course a minus a 0 is equal to 0. What is 0? This limit is 0. That is f of x minus f of a. Limit is 0. Therefore, limit as x tends to a of f of x is equal to f of a. My dear friends, if you can know this proof, you can understand the strategy in which it has been obtained. You can never forget this result. For that purpose only we have recalled the proof, that's all. Therefore, if f is derivable at x is equal to a, then f is continuous at x equal to a. Let us examine its converse. Is it true or not? Let us see. Let us now think of its converse. Consider we all know that f of x equal to mod x is everywhere continuous on R. Whatever real number you take, it is continuous on R. Well, let us test its derivability. Say at x equal to 0. I would like to calculate f dash 0, whether it exists or not. It is the responsibility is now on my shoulders to check whether f dash 0 exists or not. So consider f of x minus f of 0 by x minus 0. What is f of x? Mod x. What is f of 0? Mod 0 by x minus 0 is nothing but mod x by x. Mod x by x. Therefore, you take limits on both the sides. Limit as x tends to 0, f of x minus f of 0 by x minus 0 is equal to limit as x tends to 0 mod x by x. Well, my dear, this is a famous limit which we could have discussed for so many number of times in the limit chapter. That can never exist. To be more precise and to be more particular, the left hand limit is minus 1 and the right hand limit is plus 1. The limit does not exist at all. Therefore, limit as x tends to 0, f of x minus f of 0 by x minus 0 does not exist. Therefore, f is not derivable at x is equal to 0. That is a beautiful example to say that the converse of the previous result is not true. Okay, what is the previous result? If f is derivable, then it is continuous. Then f is continuous, it need not imply f is derivable. So continuity need not imply derivability, whereas derivability implies continuity. Well, my dear, this is not just for the sake of the converse. This educates us. From this we can learn so many things. F of x equal to mod x, continuous at x equal to 0, not derivable at x equal to 0. One more thing, f of x is equal to mod x minus 1, continuous at x equal to 1, but not derivable at x is equal to 1. F of x is equal to mod x minus 2, continuous at x is equal to 2, but not derivable at x is equal to 2. F of x equal to mod x minus a, continuous at x equal to a, but not derivable at x equal to a. You can be reusing the result. Yes, this one result can be applied recurringly. Yes, by the recurrent application, we see that f of x is equal to mod x minus a is continuous at x equal to a, but not derivable at x is equal to a. So while going through the questions which are to be given or already given in the NEET examinations or any competitive examinations, one should be aware of those functions which are not derivable or which are not continuous at the particular given or assumed points must be said on the spot itself simply by looking at them. How are they? What are they? This is one such. There might be asking one question. Consider the function f of x is equal to mod x plus mod x minus 1 plus mod x minus 2, like that, for all x belongs to R. The number of points at which the function is not derivable, that is the question. You need not proceed. You need not solve it. You need not explore it. It's very simple. This becomes 0 when x is 0. This becomes 0 when x is 1. This becomes 0 when x is 2. Therefore, the points at which the function is not derivable is 0, 1, 2. How many points? 3 points. Okay? At these 3 points, the function is not derivable. Function is not derivable. As you see, with the help of just one example, we could have enriched our knowledge, we could have enriched our ideology, so that simply by looking at the function itself, we may trace its nature. Of course, rewarding modulus. Okay, let us observe some more such examples which educate us, from which we can learn so many things. Observe the function here. F from R to R is defined by f of x is equal to x sine 1 by x if x not equal to 0 is equal to 0 if x is equal to 0. This is the function given, and regarding this function, some 4 options have been given. F is continuous at x equal to 0 but not derivable at x equal to 0. F is derivable at x equal to 0 but not continuous at x equal to 0. F is neither continuous nor derivable. F is both derivable and continuous. These are the options. All the options are just regarding continuity and derivability. Okay, we do not use the process of limits to have the continuity. As we could have already studied in continuity, x sine 1 by x is always continuous on R. Why? Because limit always exists, of course. Even though limit of sine 1 by x as x tends to 0 does not exist, as x is before that, x tends to 0 implies limit of this is 0. As this is a bounded quantity, shall we recall the theorem? F of x tends to 0. G of x is bounded. Then f of x into g of x tends to 0. Could you recollect it? Isn't it? F of x tends to 0. G of x is bounded. Then the product f of x into g of x tends to 0. Basing on that, limit of this as x tends to 0 is 0, which is nothing but f of 0. So it is surely continuous at x equal to 0. We are able to observe it carefully. X equal to 0, and all the 4 options given are about continuity and derivability at x equal to 0. Therefore, we have declared that f is continuous at x equal to 0. Now, it remains to test about the derivability of f at x equal to 0. Let us do the same. Consider why should you consider this? Among all the 4 options, he is inquiring of continuity and derivability at x is equal to 0. We could have already declared that it is continuous at x equal to 0. It is now our duty to test whether the given function is derivable at x equal to 0 or not. For that purpose, we need to find f dash 0. What is f dash 0? Is it not this limit? We are now trying to find it. How? Look here. This is equal to, what is f of x? What is f of 0? 0, leave it off. X minus 0 is x. So that what is going to remain here? Sine 1 by x. That is also a famous problem, famous function whose limit as x tends to 0 does not exist. Which does not exist. You could have observed By simply looking at the problem itself, we are able to declare that it is continuous at x equal to 0. But of course, by putting a simple and single step, we have noticed that f is not derivable at x equal to 0. Therefore, what type of function it is? It is continuous at x equal to 0, but not derivable at x is equal to 0. Now and then, he may ask you to say something. It is derivable but not continuous. Some option is also there. That is a foolish option. Why? Because if at all it is derivable, it must be continuous. Such things do not happen, isn't it? Okay. Even from this problem, we can learn so many things. What are they? A small change I would like to make to this problem. You observe it. If I write x square sine 1 by x, then what happens? This is x square sine 1 by x. 1x is only cancelled. What is there? X sine 1 by x is there. And we are sure of the result. This limit is of course 0. So we are happy. This is nothing but f dashed 0. F dashed 0. Like this, x sine 1 by x is not derivable. X square sine 1 by x, x cube sine 1 by x, x power 4 sine 1 by x, x power 5 sine 1 by x, like that. They're all derivable at x is equal to 0 also. All derivable at x equal to 0 also. Not only that, instead of sine function, somehow you may be given cos 1 by x also. Then also this function is both continuous and derivable at x equal to 0, as we are having the exponent of x is greater than 1. As greater than 1. Well, by noticing all these things, we can have a general outlook, we can have a general understanding as we are going to say. Observe the question carefully. F from R to R is defined by f of x is equal to x power n into sine 1 by x. If x not equal to 0 is equal to 0 if x is 0. It is both continuous and derivable at x equal to 0. He is giving us. In the data itself it has been provided. Then what should be the nature of n? He is asking. Less than 1? Greater than 1? Greater than is equal to 1? Arbitrary. Arbitrary means whatever value you can have. Right, you see, if x is 1, then limit exists, it is continuous. If x is greater, n is greater than 1, then only 1x will be cancelled, 1x will be remained in the numerator, isn't it? It is possible when n is greater than 1 only. N is greater than 1 only. Then only it is correct. This can be observed by means of the previous example. You could have had x square sine 1 by x, or x cube sine 1 by x, or x power 4 sine 1 by x, like that. If you have the function like that, then f is derivable at x is equal to 0 also. Therefore, in order to answer such questions, n must be greater than 1. We could have arrived at this conclusion simply because of by looking at some numerical examples in which that concept is involved. Isn't it? Well, let us now try to look at some other function from which also we can learn something. Another important concept. We have already noticed and proved that f is derivable at x equal to a implies f is continuous at x is equal to a. F is derivable at x is equal to a implies f is continuous at x is equal to a. Well, let us recall one important concept from logic, that is mathematical statements. If there is a particular implication, say P implies Q, every such implication is logically equivalent to its contrapositive. What do you mean by contrapositive? Negation of Q implies negation of P. You're not understanding? You call this statement some P, that Q. P implies Q. We have at our disposal. I call this entire thing some statement small p. Let me represent this entire thing by small q. What are you having before us? P implies Q. What is its contrapositive? Negation of Q implies negation of P. And from logic, we recall that every statement is equivalent to its contrapositive. That is, f is not continuous at x equal to a implies f is not derivable at x is equal to a, isn't it? That is, what I mean to say is, f is this is now the powerful weapon with us, which is going to be in our hands. That is, in order to test the derivability, if it is possible to notice that it is not continuous, then it is not derivable automatically. Automatically it is not derivable. As an example, you consider the function f of x is equal to integral part of x plus 1. When can you say that it is not derivable? At what points it can be not derivable? We know that at integral values of x, that is x equal to 1, x equal to 2, x or x is equal to n for any integer n, this is discontinuous. Those points of discontinuity will now be termed as the points of non-derivability, isn't it? What are the points at which the function is not derivable? It's very simple. Suppose those points at which the function is not continuous. So, if you notice that a particular function is not continuous at a particular point, surely then it is not derivable at x is equal to that point. Best example, ready-made example, you observe this, f of x equal to integral part of x. That is greatest integer function. We all know that it is not continuous at x is equal to 1, x equal to 2, x is equal to 3 or x is equal to n for any integer n. Automatically, evidently, clearly, the function is not derivable also at x is equal to n for any integer n. Yes, likewise, we may come across so many examples. Let us face some other such example. Consider the function f of x is equal to 2x plus 3 for all x less than 1 is equal to 6 if x is equal to 1, 5x minus 8 if x is greater than 1. And he is asking us about the derivability of the function f. You see, derivability means limit as x tends to 1 f of x minus f of 1 by x minus 1. A big calculation is needed. You first of all check the continuity, because it can be said simply by the observation itself. By looking at it itself, we will be able to have the continuity. You check whether it is continuous at x equal to 1 or not. Left hand limit is 5. Right hand limit is minus 3. Not continuous. Not continuous implies not derivable. This is the beautiful occasion at which we decide on this part itself that it is not derivable. On this part itself, we will be able to decide that the function is not derivable at x is equal to 1. At x is equal to 1. That is, even if you want to do, if you are required to have f dash 1 from left, that is the left hand derivative, it can also be said directly. From left 2x plus 3, derivative of 2x plus 3 is 2. You can calculate, no doubt at all. And f dash 1 from right, 5. Do you want the proof? It's not impossible. We can do. F dash 1 from left is limit as x tends to 1 from left of f of x minus f of 1 by x minus 1. What is f of x? 2x plus 3. F of 1, 6 by x minus 1. To x minus 3 by x minus 1, actually it does not exist. Let me call this phi. Then it does not exist, isn't it? Therefore, consider the famous function f of x is equal to integral part of sin x plus cos x for all x belongs to closed interval 0 to 2 pi. If you remember, we could have discussed the same problem in continuity to find the points of discontinuity. We noticed that there are 6 points of discontinuity, namely some 5, 4 and so on like that. There are 6 points there we could have done. You can easily verify in the continuity we come across this problem. But now the same problem has been asked in derivability. He is asking about the points at which f of x is not derivable. Is it a new work? No. The work has already been done. In continuity, we have noticed that there are 6 points of discontinuity, and those 6 points are again here the points of non-derivability also. Therefore, answer is 6. Answer is 6. On what basis you are able to have the answer directly? As already we could have done the same problem in continuity, and we could have traced that there are 6 points of discontinuity. Those 6 points of discontinuity again work as those points at which the function is not derivable, by simply making use of the concept that not continuous implies not derivable. Point of discontinuity implies point of non-derivability. That's all. So the answer is 6. Good.